All right, so before we get started, I'd like to thank my colleague for covering my class today while I'm at Queens College. To the rest of you, hopefully you have your iPads out and you're ready to continue as we finish up igneous rocks and get into sedimentary rocks today. All right, so once you have your notes up, take a look. We left off talking about igneous rocks and igneous intrusions, the idea that rocks are going to form inside the earth, they're going to cool slowly, and therefore they're oftentimes going to form large crystals, so like a granite or a gabbro, different rocks that we've been talking about in class. The synonym for intrusive igneous would be pluton. So we actually have a chart that you'll see in the next slide where we talk about 5 different types of plutons. So here we have a dike. Dike is going to be a vertical cut across other rock layers. Now, later on we'll learn about the different laws of stratigraphy and geology. In particular, we say that in the principle of original horizontality, horizontal being the root word there, that layers are deposited horizontally. So think left to right if you don't understand what horizontal means. Sorry about that. So if we cut across that, you're going to have a igneous intrusion that is moving upward, oftentimes at an angle. That's going to be a dike. If it's parallel to those horizontal layers, it would be called a sill. Now, where have we heard about the word sill before? Thinking about windows, right? Windows usually have that piece of wood or metal across the bottom. We call that a window sill. Think about that. It's horizontal. It's parallel to the other parts of the window that slide up and down. So in the same way, a sill in an igneous intrusion is going to be parallel to the other layers. Again, we'll see that in the diagram on the next slide. The laccolith intrudes that horizontal layer, but actually starts to push up on the overriding layers. So it creates this bulge or this dome. Oftentimes, I think about it like a mushroom. So you might, in your notes, want to just, draw yourself that little mushroom type shape, right? And if you think about that, mushroom pushes up, has this kind of dome shape. Anytime you see that, you got yourself a laccolith. Lastly, in the idea of intrusions and in this new sense of, okay, material inside the earth, you have a batholith. And a batholith is always going to be this big blob underneath the surface. It doesn't cut layers, instead it just kind of takes over the whole thing. It doesn't parallel layers, again, takes over the whole thing. So a big, huge blob of igneous rock. But now the last one, volcanic neck. This is going to be associated with where a volcano used to be. So the volcano was forming, it was erupting. At some point, some magma made it up inside there. It didn't escape out the top and hardened. It crystallized inside. So the other parts, the actual volcano, as most of us would think about, is going to be more ash and different types of pyroclastic material making up that volcano. But the actual inside part is going to be this dense crystalline rock. So let's go ahead and take a look at the next slide. This slide shows you the different types that I was just talking about, so I'm going to try and highlight them for you. We'll see how good I am today with the iPad. Over here, anytime you have a layer that's cross-cutting, 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 we call those dikes, right? Again, principle of original horizontality, those layers are all horizontal, so I'll try and highlight them as red, right? These are all horizontal. But when the dike cuts across that intrusion cuts across that, boom, we got a dike. Gonna pause real quick. I needed to get those lines out of the way so I could continue to explain. The sill that we were talking about is going to be parallel to the other layers. So you look over here where it says sill, This time I'm going to just circle it in green. And hopefully that starts to make sense. It is parallel to the other layers, just like the bottom of the window sill that you'd see in your room or in the back of the classroom. All right, 2 down. A laccolith, we said, is going to have a mushroom shape, and it's going to push up on the overriding layers. So you see how it makes that contour. And on the surface itself, we actually end up with this dome, which we'll learn about later on. All right, 3 down. Batholith, big old blob, big, huge area. Other diagrams, it could literally just be some kind of crazy old blob that just takes over a whole area, and you're like, okay, batholith, no big deal. And then your volcanic neck. The volcanic neck is what this region will become. You're all sitting there going, I'm not sure what he means by that. Well, let's take a look at the next picture. That is a volcanic neck. It's a pretty famous one. I'll reference it again. The thing that you're not seeing is that this used to be the volcano, right? But over time, weathering and erosion got rid of all this, right? So if you think the winds come, the rains pour, gets rid of all the material that would have been over here, all the material over here, and what are you left with? The crystalline rock that filled in that center part of the volcano. All right, I'll review this again on Friday, but just want you guys to understand with a couple pictures what you're actually looking at. So one of those themes I've been trying to reiterate in class is that we classify rocks, igneous, sedimentary, metamorphic, based on how they formed. So the igneous rocks all formed from a molten rock, whether we call it magma because it's inside the earth or lava because it was on the surface of the earth. But when we actually identify the individual rocks in that particular category, we want to be looking at the texture and the composition. So where I held up a piece of granite in class and we said, okay, granite oftentimes is going to be felsic, which means it has light-colored minerals, and it's an intrusive igneous rock, so it's going to have coarse-grained textures, large crystals, easy to see with the eye. This is a good way to identify each rock. So when you look down this list here, we have gabbro, mafic, dark and colored, also going to be coarse-grained because it's an intrusive igneous rock. If it was on the surface, right, if it was an extrusive igneous rock or a volcanic rock, we'd call it basalt. And in class, we tried to look at the difference between gabbro and basalt. We tried to look at the difference between rhyolite back here and the granite. They're both the same composition, but because this one was inside the earth, it's coarse-grained. This one was on the surface, it's fine-grained. Too easy? I think so. Let's keep going. Down at the bottom, you have diorite. Diorite's going to kind of be a mix between mafic and felsic. It oftentimes has like a speckled look to it. And your diorite, intrusive, andesite, extrusive. There you guys are thinking, okay, so same composition mixed between dark and light minerals, and then is it coarse-grained or fine-grained? I apologize for saying the same thing over and over again. Let's keep going. So sedimentary rocks are formed through a sequence, right? We need, first off, weathering and erosion to get us a group of sediment. And when we did the lab, we looked at starburst getting cut up, right? That made us the group of cut up pieces of starburst or sediment, right? Now the sediment needs to get buried. So first we need to make a pile of it called deposition. It needs to get buried. And then as you pile more and more material on top, first you're going to compact it. So you're going to press it tighter and tighter together. And then particles will actually glue together with a cement. So So now once it's cemented, we call it a sedimentary rock. But what are some of these sediments that we could be gluing together? Well, we're going to see tomorrow as I pass around some different samples that you could have a pile of seashells, right? Broken up seashells, that's your sediment. We glue it together, we make a rock called coquina. We take a bunch of sand grains, we glue them together, we make a sandstone. Take a bunch of pebbles, some smaller rocks with some mixture of sand, we glue those together, we're going to make a conglomerate. So there are going to be a bunch of different rocks we look at in the sense of a sediment or clastic sedimentary rock. But other times we might actually, through chemical processes or biological processes, form different types of rocks. So that's where coal comes in, right? Coal, if you're not familiar, is made of dead plant and animal remains that gets packed together in an anoxic environment, meaning that there's no oxygen there for it to decay, and therefore it gets preserved real tight. Coal, by the way, is pretty important. It's how we have a lot of our electricity. So sediments, as we said, can be clastic or fragments of other rocks. By definition, a sediment is going to be a loose, unconsolidated deposit of weathering debris, chemical precipitates, or biological debris that accumulate on Earth's surface. Wonderful definition. These different sediments, we classify them kind of by grain size. So when we talk about pebble or sand or silt or clay, we're talking about how large are the actual sediments or clasts that we're observing. In a similar way, as I said, with a coal, you're dealing with dead plant and animal remains. That's going to be your organic material. If you remember back to the minerals chapter, we said inorganic means was not once living. So organic then would be was once living, or the remnants of living organisms. Chemical precipitates, though. Chemical, we're thinking not living material, not crystalline rock, but instead oftentimes ions that are dissolved in different fluids now start to fall out of solution when there's too much for the solution to hold. So it's saturated in the case of salt. Or you drive off the water and what's left behind. So the idea of like an evaporate, if you drive off all the water, what's left behind is going to be your precipitate. And that's actually where we get the rock salt. So all that wonderful salt that they poured out on the roads last week so that we didn't slip and slide, that came from a mine. That mine is the remnant of ocean water that continually would evaporate off, and the salt left behind would just make these nice parallel beds that then could grow further and further. And we, of course, go in now, we mine it, it's quite profitable, and chuck it around on the roads. Or we clean it up a little and put it on your table as halite, or table salt. Cool. The physical and chemical weathering breaks rocks into smaller and smaller pieces. This is where we get our sediments from to keep this whole process going. Ah, that's where I left that quarter. Just kidding, that quarter is there for scale. A quarter is 1 inch in diameter. So when you look there, it gives you an idea of how large are those different grains. That's a really coarse sand on the left-hand side, tapering down to a really fine sand. Again, running this idea that the different sediments, we describe them based on how large they are. Again, pebble, sand, silt, clay, in a decreasing size. All right, 3 classifications of sedimentary rocks. So the first up would be your clastic sedimentary rock. These are going to be the ones made from chunks of other rock, whether it's an igneous rock, sedimentary rock, or metamorphic rock. If we weather it, we break it down into smaller pieces, we erode it, we collect it, right? Make a pile, deposition. Now we can start to glue these things together. When we say that sediment is moved by streams or rivers or glaciers, we can also do it with wind. These are your agents of erosion. Your agents of erosion. Very important. That's going to come up. It's going to be a theme throughout the next few chapters. So when we say wind, water, ice, those are your agents of erosion. Wind, obviously. Water could be streams, rivers, little creek. And ice, always going to be your glaciers. Now, as we transport those grains, they're going to get bopped around, right? They're going to bounce into other grains. They're going to roll along the bottom of a stream, crash into other samples, whatever it might be. That's going to cause the grains to become rounded and smoothed over. So we said at the beach, right, you go down, you collect those rocks that right along where the water's crashing, they tend to be rounded over, pretty smooth on the feet. In the same way, river rocks oftentimes are rounded over because they've been churning in the river. When you get those floods, they bounce around a lot more. When it's more of a dry spell, drought, they tend to just sit there and the water passes over. Maybe other rocks or sands or silts erode them. But that smoothing process tells us part of that story. And when we find a sedimentary rock that doesn't have rounded grains, instead has angular grains, we know that those rocks broke down, got buried very quickly, and didn't have time for transport to take place. So kind of tying back to what we said when we started the chapter, rocks have a story to tell. And this is just another way that you guys are going to learn how to read those stories. Sorting occurs when streams and rivers enter large bodies of water. When the stream's flowing along, its velocity directly affects the grain size that it can carry. So the faster the water is moving, the larger the grain it can carry. If it starts to slow down, well, then those larger grains are going to fall, and maybe it can only carry pebble or sand or silt, or maybe it's moving real slow, it can only really carry the clay. Well, just as I'm describing that, hopefully you're able to picture that the velocity is going to decide what can be carried and what needs to be placed down. Well, if the stream or river flows into a large body of water, it's going to slow up. Like when you try and walk down the freshman hallway coming from lunch. Suddenly you hit this like wall of kids. You can't move as fast. It just happens. So the water, as it slows, starts putting stuff down. The large things are going to be placed usually in that opening of the channel, and then it gets smaller and smaller and smaller as you move away from the entry point. So that's some natural sorting. That, again, comes back to that story when we see the sand collecting, right? We know, okay, if we have a sandstone, that was probably where the beach area was. If we have limestone, that was probably formed out on the shelf, further and further out into the water, because that was when the clay was able to actually settle down. When water flow decreases, heavier sediments fall out of suspension. Sorted grains become cemented from smaller grains filling in their pore spaces. There's a lot of repetition. I do apologize. Now, let's talk about cementation. Cementation is when minerals fill in the spaces between grains and bind fragments together. When I think bind together, I think glue. This is the glue that holds all the grains together. Just like if you look at the cinder block walls above the whiteboard, right, there are these big blocks, and then there's a cement that holds all those wonderful cinder blocks together. No cement, the whole wall would fall down, so that would be a problem. No cement in these rocks, you just have a pile of sand. And there are different types of cement, which then are going to affect not only the color, but how we classify different types of sandstone. So if we have a sandstone that's rich in quartz with a quartz cement, well, that's easy. We have a quartz sandstone. If we have a sandstone that has a cement that's rich in feldspars and iron oxide, that's going to have a Arcos cement. And that's actually the sample that's sitting up on the front counter that we passed around, or somebody walked it around in class because it's so stinking big. The last one being a gray whack. We'll talk a little bit more about that when I'm in class. I'll show you guys a sample of that. Now, again, the idea of sedimentary rock is the result of weathering, breaking rock down, erosion, deposition. I can't reiterate this enough. If you guys can place the processes with the types of rock, it's going to help you guys to sort them out. And it makes it a little bit easier when you're looking at the individual samples in lab for being able to identify them. So speaking of processes, when you guys start to explore, hopefully you do some online practice tests, maybe you watch a video here or there to add to what you're looking at, and in that quality reading that you've all been keeping up on, we have things like lithification. When we say sedimentation, we said, okay, sedimentation was compaction and cementation kind of put together. Lithification is like the quick overarching idea that you convert sediments into sedimentary rock. So lithification, kind of a synonym with sedimentation, and you're going to see both of those on your tests or quizzes, so just be familiar with it. Well, what happens when we start making these sedimentary rocks, right? Because we had the burial, we had the compaction, the cementation. Now we have a layer of, say, sand that has now been lithified or cemented together into sandstone. Well, that creates a bed. And when we look out in the rock layers, or what we call bedding, right, this is a layer of sediment that's distinguishable from the layer above and the layer below. Now, sometimes that could be a foot thick, 6 inches thick, or it could be 100 feet thick. It all depends on how long that depositional environment lasted. Again, that's that third eye of our science that I was talking about, being able to read the rocks, being able to look at the individual beds and understand what was necessary to form that bed. And therefore, if we know how old those rocks are, we actually understand what that environment must have been like at that point in time. Underneath bedding is the result of compaction, right? Squeezing things together, usually because of burial, and cementation. Cementation, right? The binding, the gluing together. Right? I know, it's repetition, but hopefully it works. Now, I've been talking a bit about the different types of clastic. Let's look at the bioclastic and the chemical sedimentary rocks. Right? So if it's bioclastic, it means that there must have been organic material, usually plants, involved in the makeup of that rock. But it could also be seashells, right? In the case of coquina, where we're going to take seashells, usually they're broken up, they get stuck together, make some pretty cool looking rocks, but because there was material in there from living things, we call it bioclastic. Chemical sedimentary rocks, though, as we mentioned before, are going to oftentimes be the result of chemical precipitates, like your rock salt and like limestone. So, before we wrap up for today, quick diagram for you to look at. This shows you some of the different types of sedimentary rocks that you have, right? Conglomerate, breccia, sandstone, siltstone. Gives you the idea that, okay, as the grains get smaller, we just match up with the grain size and we can actually identify each type of rock. So when I passed the conglomerate around, you were able to see pebbles, larger grains, and they were rounded sediments. That's exactly what this chart's trying to show you, right? Conglomerate, larger grains, rounded. If they're still angular, as you guys will see on Friday, right, we call it breccia. And breccia is going to be angular grains. They're still going to be large, right? Angular sediment. The next step down from there would be a whole collection of sand. You look at it closely, you see the individual grains of sand. Maybe you knock it around on the table a little, and it looks like pieces of sand breaking off. Well, that sand size is really easy to then call it sandstone. Silt and clay, obviously, moving right down the list. But this, I think, is a little bit easier, right? All those words, or I could just show you a picture. Take a whole bunch of gravel, right? Pebbles, cobbles, and if they're rounded, they're going to make a nice conglomerate. Take a pile of sand, it's going to make sandstone. Take a whole bunch of silt, going to make siltstone. And clay, I know you're all like, claystone, nope, shale. So I waited on the last one because it's a little bit easier to see here. Clay's so fine that oftentimes you're not able to see the individual grains, but you can actually sense it, and I'll show you guys how to do that on Friday. That'll be fun. All right, and there are some happy little pictures. Again, when I said breccia before, the breccia is going to have that angular grain, whereas the conglomerate has more of a rounded grain. Your sandstone, nice little layers, and that is a pretty piece of sandstone. I won't show you anything that nice. I apologize. And then your siltstone over here, and your shale. You guys are going to see a couple pieces of shale, and then we'll actually focus on shale when we look at metamorphic rocks, because shale has like 3 different layers of, or different grades of metamorphism that can happen. So we can go from shale to slate to something called phyllite, all the way out to schist. So that's going to be a fun sedimentary rock to watch its progression as a metamorphic rock. All right, guys. With the remaining time in class, I'd encourage you to finish up your vocabulary, because you're going to want to turn that in tonight. And we're going to read the next section. So go ahead and check your backpack. Again, thank you to my colleague for covering class today. Hope you all have a great day.